Kaylee, where did you drop your Google Drive link at?
It should be in the chat here.
Let me see.
Oh, I sent it just to, sorry, I sent it just to Colton. That's my bad. Dang it, it says you need permission to open it? Yeah, you're really special. I accidentally just sent it to you. Okay, hold on. All right, I changed it to anyone with the link. Hopefully that works. So I'll drop this. Someone let me know if this works, and I'm gonna send it to everyone this time. Okay, let me know if this works, guys. If it doesn't, I'll try to fix it, but.
Looks like it's working.
Yeah.
Okay, sweet, perfect. Okay, so let me do 60 through 62. Finally, we're almost there. Okay. All right, let me share my screen. Actually, this works out because on the Jamboard, someone asked me to do a harder example of logarithmic differentiation, and that happens to be what 60 is. So this is perfect. Okay. All right, also feel free to stop me at any point if I say something that doesn't make sense or don't explain something well, or you're just confused. This is totally your guys' time and you're choosing to be here, so I'll do whatever you want to see. So, okay, question 60. So use logarithmic differentiation to find the derivative. Okay, so logarithmic differentiation is a method that we use to kind of make like taking the derivative a little simpler. And it uses properties of logs. So one of the things you do first is you take ln of both sides. Usually by taking ln of both sides, you're able to use some properties of logs, and that will help you kind of simplify your expression that you're working with. So first step, take ln of both sides. Okay, so let's do that. And yes, it's going to be helpful to remember any of like your algebra principles about logs, because that's ultimately the goal, is to try to use ln to like simplify these expressions. So try to remember any of those properties of logs. So first step, take ln of both sides. So ln of y is equal to ln of this whole thing. 3x squared minus x plus 7 to the fourth over the square root of x to the fourth plus 8x squared plus 5. Okay, so one of the properties of logs from algebra is that if you have like ln of two things like being divided or like a fraction, you can split those up over subtraction. So I'll write this off to the side, but like ln of a over b is equal to ln of a minus ln of b. So if you have a fraction, ln of a fraction, you're able to split it up over subtraction. So let's apply that here. So I get ln of y is equal to ln of 3x squared minus x plus 7 to the fourth. And then I subtract from it ln of x to the fourth plus 8x squared plus 5. Okay, so another property of logs is that if you have an exponent within the log, you can bring it out front. So I'll just write this up top again, but like ln of like, I don't even know, a to the x is equal to x ln of a. So you can bring that exponent just out front, completely out of the log. So let's do that here. But what's important is that everything in the log is raised to that exponent. So everything that's in ln will need to be raised to the exponent in order to bring it out front. You can't just have like one term is raised to some exponent and then you bring it out front. It has to be every single thing. So this works out in our case because we have this whole expression raised to the fourth power. So I'm going to bring it out front, and I get ln of y equals 4 times ln of 3x squared minus x plus 7. And then off first glance, you might not think that I can do it for the second one, but remember that a square root is just like raising it to a 1/2 power. So I'm going to do the same thing. And I get minus 1/2 ln of x to the fourth plus 8x squared plus 5. Okay, so this is a little simpler. It may not look much better, but it will be much easier to take the derivative of this. So whenever you use logarithmic differentiation, you'll have to take the derivative of both sides, which means you will have to use implicit differentiation. So it's kind of like combining some concepts that we've learned here. So let's take the derivative of both sides. So the derivative of ln of y is going to be 1 over y. And since we're doing implicit differentiation here, whenever we take the derivative of y, we have to multiply it by dy dx. All right, now let's tackle the right-hand side. Okay, so we're going to have to use that definition of how to take the derivative of ln again. So this one might be a little more confusing because it's a chain rule. We don't just have like ln of x, we have ln of 3x squared minus x plus 7. So this is going to be a chain rule here. So the chain rule says that, I'm just going to pull this 4 out here, but the chain rule says that we do 1 over 3x squared minus x plus 7. And then we have to remember to multiply that by the derivative of what's inside this log function here. So does anyone want to give me the derivative of this inside piece, the 3x squared minus x plus 7?
6x minus 1.
Yep, perfect. So times 6x minus 1. Also, I meant to say, if you also have any questions, you can definitely chat it to me as well. I keep a pretty good eye on the chat, so I should see it. Okay, so let's do the derivative of the next piece. So just gonna put some parentheses here to make it clear. So to do the derivative of ln of x to the 4th plus 8x squared plus 5, same process, chain rule. So we do 1 over this whole thing. And then we multiply it by the derivative of this inner piece. So who wants to give me the derivative of the inner piece this time?
Uh, 4x to the 3rd plus 16x.
Yep, perfect. Okay, great. So now we've taken the derivative, but our next step is to solve for this dy dx here, because we differentiated implicitly. So whenever you do that, your end goal is to solve for what dy dx is. So this is kind of a big, ugly mess right now. So let's just make this look a little nicer before we do that. So I have 1 over y dy dx is equal to 4 times 6x minus 1 over 3x squared minus x plus 7 minus, and this is 4x cubed plus 16x over 2 times x to the 4th plus 8x plus 5. Okay, so that looks a little nicer at least.
Is that x squared? Sorry.
Which part?
After the x to the 4th.
X to the
Plus
4th.
8x.
Oh, yes, it should be. My bad. 8x
Good.
squared. Thank you. Yeah, perfect. If you catch my mistakes, please let me know. So it's perfect. Okay, so like I said, we're solving for dy dx. So to do that, we need to get rid of this 1 over y. So we're just going to multiply both sides by y. Let's do this in another color so you guys can really see what I'm doing. Okay, so this becomes dy dx equals y times 4 times 6x minus 1 over 3x squared minus x plus 7 minus 4x cubed minus 16x with 2 times x to the 4th plus 8x squared plus 5. Okay, so at this point you're basically done, but there is one last step that I don't want any of you guys to forget. And that's that we want to plug in what we know y is equal to. So we actually start off the problem being told what y is equal to up here. We're told that it's equal to that whole ugly mess there. So your last step should be to take that whole thing and just plug that in for y. I would normally rewrite this and plug that in, but it's really ugly and I'm kind of running out of space. So I will let you guys finish it off and just literally write that for y and then keep the rest the same. And that would be your final step for this problem. All right. Obviously you could like simplify this a little. So you could do some simplifying here and like make it like of these terms here. I'm not gonna like do that, but always try to simplify if you can. So I think here you could like, you could pull out a 2 on top and like cancel it out. You can pull out a 4. So you can always simplify. All right, any questions on number 60? I'll give you guys just a second to copy that down, take a screenshot, whatever you want to do. Okay, so I'm going to move on to 61 now. This one is another logarithmic differentiation problem. It's a little bit shorter than this one that we just did, but still a good one to do. So let's go ahead and do 61. I'll do a different color. Okay, so just like the problem that we just finished up, like I said, your first step is to take ln of both sides, and then we're just going to use one of the properties of logs to kind of simplify things a bit. So if we take ln of both sides, we end up with ln of y is equal to ln of sine of x to tangent of x. So there's a, oh, actually, we just used this property in the last problem. So if we have a log, we can pull the exponent out front, this property that I wrote up here. And we're going to use that on this question. So this becomes ln of y is equal to tangent x, because I'm going to pull out that exponent or that power. Yes, even if your power is tangent of x, you can pull it out. You can pull out anything that's an exponent as long as the whole thing inside the log is raised to that exponent. Okay, so now all we have to do is take the derivative. We've simplified a little bit and we're able to take the derivative of this piece. It might not look super nice, but we can do it. So if we take the derivative of the left-hand side, which is ln of y, just like the last problem, this is 1 over y. But since we took the derivative of y, we add on the dy dx. All right, this side might look a little complicated here because there's some stuff going on. So first of all, we have a product rule because we have one function multiplied by another function. But this function right here is actually a chain rule because it's a composition. So we have a product rule and a chain rule. So this is a good problem to do to kind of like test your skills with derivatives. So this will really show you if you can combine the rules and you know how to like, use them all together. So let's do the product rule. So the product rule says that I leave the first function alone. So just copy it down and then we multiply it by the derivative of that second function. So the derivative of ln of sine of x is 1 over sine of x. And then because we have a chain rule here, because it's a composition, we need to remember that we have to multiply this by the derivative of sine of x. So who knows the derivative of sine of x?
Is it cosine of x?
Done.
Yep, perfect. So we multiply this by cosine of x. I'm just going to scroll over. Okay, but we're not done because we were doing a product rule, so we have to add to it. And this time we take the derivative of tangent of x. So who's got the derivative of tangent of x for me?
Secant squared of x.
Yep, perfect. Secant squared x. And then we just leave the second function alone and multiply it by ln of sine x. Okay, so let's see, can we write this any nicer? I'm thinking here. Ln. Think we can. Oh, there's a chat. Okay, this is a good question. If you did the product rule in the opposite order, would you get the same answer? Yes, you would get the same answer. So the product rule is nice because it is addition in between them. So the product rule says that if you're doing like the derivative of like f times g, this is f g prime plus f prime times g. If you did that in the opposite order, you'll get the same thing. That's because multiplication is commutative and so is addition. So it doesn't matter. You could do that. You could literally do f prime of g plus fg prime. Doesn't matter what order you do it in, as long as you do both steps. So that's kind of the difference between like the product rule and the quotient rule, where the quotient rule, it matters exactly what order you do it in. That's why we have that fun little jingle of the low d high minus high d low over the square of what's below. But product rule doesn't matter. You can do it in either order. So honestly, sometimes I probably accidentally do it in the reverse order because I'm just like going through it, but it doesn't matter. Okay, so that was a good question. I'm trying to think if I can simplify this before I do anything else. Let's see. So this becomes 1 over y dy dx equals tangent of x times cosine over sine plus secant squared x times ln of sine of x. Okay, anyone have any ideas for what we could do here?
We could simplify the cosine x over the sine x into cotangent of x.
And then what else could we do? If anyone has any ideas. Oh, I think there's a chat. Oh, someone sent the link to the Jamford. Yeah, good. So this is 1 over y dy dx, and then this is tangent x times like tangent inverse, I guess. Oh, cooler, I'm sorry. Plus secant squared x times ln, oops, of sine of x. All right, anyone see anything here? Oh, there's a check. So why doesn't the tangent x go with the cosine on top of sine x? You could totally do that, and I mean, it's not wrong. It's just cosine over sine can be simplified. It's just a matter of getting the simplest answer. But you could do that. So you could totally do this instead. So you could do tangent x cosine x over sine x. Doesn't matter. It would still simplify to like the same thing that I just had, but this. Okay, so we'll just leave it as this. It's just a matter of simplifying. So if you want to solve for dy dx now, we can multiply both sides by y.
What? I'm freaking out.
So then this becomes dy dx equals y times tangent x cosine x over sine x plus secant squared x times ln
I feel like I missed a lesson looking at all this.
of sine x. Is everyone okay? I can hear someone's audio. Okay. So now we've solved for dy dx because we implicitly differentiated. And then just like on the last problem, your last step is to plug in that like function that you started out with. So plug in what y is. Oh my gosh, for y. Wow, that was a really long arrow. And then you're done. So to recap, there's like a few steps for implicit differentiation, or I guess logarithmic differentiation mixed with implicit. So logarithmic differentiation, start by taking ln of both sides. Use any properties of logs, maybe simplify the way things are written. So either like pull out an exponent, split it up over subtraction, and then implicitly differentiate. So once you've taken ln of both sides, it's really just a matter then of differentiating the whole thing. And then you'll just take it from there with implicit differentiation, and then you can solve for dy dx. Anyone have any questions on like that process?
So cotangent times tangent equals 1, right?
Yeah, that's what I was getting at earlier. You could plug in 1, but I felt like I was confusing everyone, so I just thought I would go through the process. But yes, this is just 1. So this would be, let me zoom out, sorry. This would be dy dx equals, and then if I plugged in the y, I would have sine x, tangent x, and then here I would have 1 plus secant squared x times ln of sine x. Yeah, that's what I was getting at, that you could simplify that to be 1, but I felt like I was just confusing everyone. So I didn't want to like get stuck in the simplifying and then kind of confuse the differentiation part. But yes, good observation. Okay, anyone else have any questions? Good catch though. That is 1. It does simplify down to 1. Okay, let me check the Jamboard if there's any other questions. So that was an example of logarithmic. Someone said questions 2 and 3. Someone does want me to do 62. It's pretty quick. So I will go ahead and do 62. Okay, so we didn't do anything like 62 in recitation. 62, it says to find the derivative of the inverse of g of x equals 2x cubed plus x plus 2. We didn't do anything like this on our worksheets, but I know that probably at least one of my classes learned this in their lecture. I'm not sure if both of you did, considering one of my classes didn't even have this chunk of the study guide. But we'll just go ahead and do it anyways, because it doesn't hurt to know a little more. So there's a process to doing a problem like this where it says find the derivative of the inverse. So if you think back to algebra, maybe a long time ago, but if you were given a function and you were told to find the inverse, your first step would be to switch all the x's and make them y's, and to switch all the y's and make them x's. I don't know if anyone remembers that, but like if you had f of x equals this, you would change all the x's to be y's and all the y's to be x's, and then you would solve for the y. Hopefully that rings a bell, because it's kind of a similar start to these problems. So when it says to find the derivative of the inverse, you're going to have like the same first step kind of as you would do in algebra. So let's, oops. All right, okay, so let's write this as y equals 2x cubed plus x plus 2. If you ever have f of x equals something or g of x equals something, it's the same as just writing y equals that. So for this purpose, I'm just going to write y equals to this function. So your first step, like I said, similar to when you would do it in algebra, is to just change all the x's to be y's and y's to be x's. So this becomes x equals 2y cubed plus y plus 2. And there's a chat, so give me a second. So someone asked me about implicit differentiation. So a lot of the times with implicit differentiation, I'm trying to think of past problems we've done. I've really seen mainly the y be plugged in when you're doing logarithmic differentiation. I'm trying to think if there was ever an example where we plugged something in for y in the past. I think it was just when we were doing logarithmic differentiation when we would plug back in what y is. So yeah, I don't think in the past when we've done it that we've ever done that before. So I think my safe answer is probably just when you do logarithmic differentiation. It's like the only time I've seen us do it in worksheets to plug y back in at the end was the question. Okay. So like I said, for this problem, you switch the x's and the y's. And then after that, your next step is just to take the derivative of everything. So you're just going to take the derivative here. And yes, because we have, we're taking the derivative with respect to x of this thing, and we have y's on the other side, we will have to implicitly differentiate. Actually, this is kind of a good example for the question that was just asked. Okay, so the derivative of the left-hand side is just going to be 1. The derivative of 2y cubed. Does anyone have the derivative of 2y cubed for me?
6y squared.
Perfect. 6y squared. And then since we took the derivative of y, I'm going to write dy dx. And then the derivative of y would just be 1. Same thing, dy dx. And the derivative of 2 is just 0. So now we just need to solve for dy dx. So I'm going to move up here, but this is 1 equals, and I'm going to pull that term out. And then I'm going to solve for dy dx. Sorry. 1 over 6y squared plus 1. And that's it. Okay, so if you're asked to find the derivative of the inverse, you kind of have an extra step as opposed to just like finding a derivative. So if you're asked to find the derivative of the inverse, your first step is to switch the x's and the y's, and then your next step is to differentiate. And that's because like if you think about inverse functions, so with regular functions, you go from like the domain to the range. If you have an inverse, it just goes from the range to the domain. So it kind of does the opposite that the original function does. So when you're doing the inverse, you can think of it as like, oh, I switched my x's and my y's. Because it's kind of doing the opposite of what the regular function does. That might make a little bit of sense, might not, that's okay. So that would be your first step for this, and then you take the derivative, which you'll have to do implicitly, and then you're done. Okay, I think the next questions were 2 and 3. Also, that's the last question on here, so if you have more questions, feel free to add them because I will just go through whatever you guys ask me to. Okay, let's see. Okay, so scroll up to questions 2 and 3. Okay, here we go. Okay, so for 1, 2, and 3, yeah, 1, 2, and 3 say using the definition of the derivative, find the slope of the tangent line. So we are trying to find the derivative here using the definition. So this is very key. I know a lot of you would look at this problem and you would probably say, okay, well, this is equal to x to the 1/2 power. And by the power rule, I know this is 1/2 x to the negative 1/2 when you take the derivative. And then that just becomes 1 over 2 square roots of x. Done. Yes, that was very simple and that was very quick, but that is not what the question is asking you to do. And I have seen this time and time again where this question is on the exam. A lot of students will just use the shortcut to do it, and you will not get points for doing that. You know, it's kind of frustrating because it's like, we've just learned this shortcut. Why do we have to go back to doing it the long way? I know, it's frustrating. But if it asks you to use the definition of the derivative, do it. Just do it. I promise it will be worth it. I hate to see you guys get like no points just because you accidentally use the shortcut. Use the shortcut to check your work. That's always a good idea. So if you go through using the definition of the derivative, maybe then afterwards use the shortcut and check and make sure you got the same thing. Because if you use the definition of the derivative or the shortcut, you should get the same thing. So that's an idea, but do not just do these 3 little steps of work. They will not get you anything. I mean, they could get you a point. I don't know. I'm not the grader, but they won't get you much is what I'm saying. So, okay, the definition of the derivative is given up here. It's that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, so let's go ahead and kind of plug in our function for that. So f prime of x is equal to, so I'm going to erase this just so no one accidentally sees this and thinks that that's what I was saying to do, because don't do it. So f prime of h is equal to the limit as h approaches 0. And then our first thing is f of x plus h. Okay, so let's take our function f and evaluate it at x plus h. So that is the square root of x plus h. And then we subtract from it f of x, which is the square root of x, all over h. I know it feels like it's been forever since we've done limits, but here we are again. Okay, so think back to when we like first started doing limits and we had square roots in what we were trying to evaluate the limit of, and we had a few techniques that we would use to kind of get rid of these square roots. And one of those things was multiplying by the conjugate. So let's try multiplying by the conjugate here. And that's because our first technique was always just direct substitution and to just try plugging 0 straight in. But if you tried plugging 0 in for h here, you would get 0 over 0. And that's not something we want. So remember, if we ever try to just plug it in directly and we get 0 over 0, we've got to do some manipulating in order to get the correct answer. So let's try multiplying by the conjugate, which is always a good idea if you see square roots. Never a bad idea. So multiply it by x plus h. And remember that the conjugate just switches the sign between these two things. So instead of instead of the square root of x plus h minus square root of x, this becomes plus the square root of x. And if you don't remember, hopefully you'll see why that's a nice thing to multiply by. Also, just going to throw in this reminder, remember to carry through your limit until you have evaluated it. Don't drop it. Just don't do it. It's another one of my warnings. So this is still the limit as h approaches 0, except now I'm going to simplify a bit and multiply my numerators here, and this just becomes x plus h minus x over h times the square root of x plus h plus the square root of x. Okay, well, this is just the limit as h approaches 0 of h over h times the square root of x plus h plus the square root of x. So usually when you're doing things like this, at some point you're able to kind of like cancel out an h on the top and the bottom. I won't say always, but usually at some point you're able to do that. So here we have a h and they cancel out. So once again, I am carrying my limit notation here. So this becomes 1 over the square root of x plus h plus the square root of x. Okay, so now we are finally at the point we're going to evaluate this limit and we're going to plug in 0. So now I can drop my limit notation. So as soon as you plug in a number, you can drop it. Before then, don't drop it. So until you evaluate it, keep it there. Because if you drop it, you're kind of like saying, oh, I've already taken the limit, but you haven't. So it's technically not a correct statement. So we'll plug in 0 now and we'll get 1 over the square root of x plus the square root of x, which is 1 over 2 square roots of x. Okay, so my warning at the beginning, if you see this problem, do not use the shortcut. I swear it will not get you very far with points. You will get the right answer, but you won't get very much for it. But like I said, if you do the definition and you want to check your answer, feel free to use the shortcut to check your answer. So I'm going to check my answer, and I'm going to take the derivative of the square root of x using like our little shortcut. So this is equal to x to the 1/2 power. So I know that I bring the 1/2 in front, subtract 1 from my power, and this becomes negative 1/2, which is just 1/2 square root of x. So yay, we got the same answer. That's great. So if you're ever asked to use the definition, feel free to use the shortcut to check, because you should get the exact same thing. So if you do your shortcut and you don't get the same thing, there's probably an error going on somewhere, whether you took the limit wrong or you just did the shortcut wrong when checking it, but they should equal each other. So you don't have to check it, but if you want to, that's a quick way to do it. Okay, so I think I was asked to do question 3 as well. Oh wow, there's a lot of questions now. Okay. Okay, so let's do 3 next. Also, if anyone's just now coming in, I'm gonna drop a link here for some things. Okay, so I have been using a Jamboard for questions. So if you follow this link that I'm about to drop, you'll be directed to the Jamboard where you can put some questions on sticky notes. And then I'm also going to drop another helpful link. And this is just to a Google Drive. This has the full study guide answers in them. It also has my Jamboard in it. And then it also has this little like PDF that I made that has a bunch of theorems from chapter 3. So I put a bunch of theorems from chapter 3 on there that like I've used in recitation because I feel like they're helpful. So if you're just now coming in, there's 2 links. Okay, so let's go back to doing questions. So question 3, or does anyone have any questions on number 2 first before I keep going? Okay. All right, so let's do question 3 now. This is another definition of derivative, so I'm just going to move my work over and kind of in the way. Okay, give myself some space here. Okay, so another definition of derivative using this f prime of x equals the limit as h approaches 0 thing. So let's go ahead and just do the same process, but with a different function. So we have f prime of x is equal to the limit as h approaches 0. And then we have to first do f of x plus h. So we're going to do our function evaluated at x plus h. So this would be 2 over x plus h. And then we subtract f of x. So subtract 2 over x. And then h goes on the bottom. Okay, so just like in the past problem, how I said, oh, you know, if you have some radicals, some square roots in your thing, maybe multiply by the conjugate, that's always a good idea, because then usually that tends to eliminate some square roots, manipulate some things, and you're able to actually take the limit. A similar concept here, so if you're ever dealing with like fractions in fractions, it's never a bad idea to try to, you know, get rid of the fractions in the fractions. And what I mean by that is make it so that you just have a single fraction, not fractions in the numerator. So it's never a bad idea to kind of like get a common denominator, multiply by something so that you have something a little easier to work with. A lot of the times that will help you take the limit. So remember though, the reason that we do that is because if I were to plug in 0 for h right now, I would get 0 over 0. And that's not what we want. So if you're ever taking the limit and you just direct substitute in, you know, whatever h is approaching, and you get 0 over 0, we don't want that. So we want to do some manipulating so that we have something a little easier to work with that doesn't give us 0 over 0. So we've got some fractions here. So I'm going to suggest that we multiply the top and the bottom by a common denominator. So a common denominator for these 2 fractions in the numerator would be x times x plus h. So I'm going to suggest that we multiply by x times x plus h over 1, and then same thing in the denominator. So remember just some like rules of algebra, whatever you multiply in the top, you also have to do in the bottom, because we want to make sure that we don't change what we have here. So as long as we multiply by the same thing on top and on bottom, we're good. Okay, so I'm gonna, oh, sorry, there should be a multiply sign there. So I'm gonna go ahead and like do out step by step. That way, hopefully everyone sees what's going on. So this is equal to the limit as h approaches 0. Notice I didn't drop my limit yet. So this becomes 2 times x plus h over x plus h minus 2 x plus h over x all over xh times x plus h. Okay, so I wrote these steps out so everyone could really see what's going on here and why this works. So if you notice here, we're able to cancel that out, and then here we're able to cancel that out. So multiplying by a common denominator will always wipe out the denominators of your fraction because you're able to cancel things out. So this becomes the limit as h approaches 0 of 2x minus 2 times x plus h all over xh times x plus h. Okay, so let's do a little bit of simplifying in the numerator here. So I'm going to jump down here. So this is equal to the limit as h approaches 0 of 2x minus 2x minus 2h over xh times x plus h. Okay, well, my 2x minus 2x goes away. And then this becomes the limit as h approaches 0 of negative 2h over xh times x plus h. And I'm writing out a lot of steps just because I want everyone to make sure that they're like following what I'm doing. But obviously you can kind of skip some of these steps if you don't need to see it all in your work, but it always helps to make sure that you don't make any mistakes to really, you know, take it step by step. So now I can cancel these h's out, and this becomes the limit as h approaches 0 of negative 2 over x times x plus h. Woo, we finally made it. So now we've got something nicer, and if we plug in 0 for h, we will not get 0 over 0, which is what we were going for. So I'm going to evaluate it. So now I plug in 0 and I drop my limit notation. So this becomes negative 2 over x squared. Okay, just like before, why don't we check our answer using the shortcut? So I'm going to come up here and I'm going to check my answer. So f of x is also equal to 2x to the negative 1. So if I took the derivative, the derivative of this using the method, the fast shortcut, the power rule, this means that f prime of x would be negative 2x to the negative 2, which is the same as negative 2 over x squared. And voila, we get the same thing. I know you're probably thinking the thing every calculus student thinks, and you're like, that took me 3 seconds, and this other method took us 10 minutes. I know. Believe me, I feel the pain, but you got to do what you got to do. And sometimes you got to go back and use the definition of the derivative and where it comes from and the limit. That way you demonstrate that you know what you're doing and that you've learned some calculus. So unfortunately, it be that way sometimes. So, okay. Let me check the Jamboard for questions. Okay, so I'm going to move some of these questions around if I've done them. Oops. Okay, so someone asked for number 7. Let me just look at number 7 really quick. Oh, okay. So someone wants to know why number 7 says that it's correct. So let's do that one because that one's not too long. Okay, so questions 6 through 7. Well, actually, does anyone have any questions on like the definition of the derivative or anything that I just talked about before I move on? Because I might not come back to it. All right, so 6 through 7 give you the derivative of a function, and it wants to know if the following simplification is correct or incorrect. So if you can't tell by now, something that we do a lot in recitation is focus on simplifying things. So we always want your answer in simplest terms. So this question is just kind of testing you to see if you can follow someone's steps and see if they simplified correct or not. It's always harder to look at someone's work and pick out the mistakes because sometimes you just kind of follow it and you're like, yeah, that's right, even though it's not. So this is a good test to see if you actually know how to simplify something well, to just see if you can catch mistakes or not. So let's do question 7. So, all right, so we start out with f prime of x is equal to x plus 1 times 2e to the 2x minus e to the 2x over x plus 1 squared. Okay, so if I'm just following this work that's down here below from this step to this step, it looks like they pulled out an e to the 2x. So let's see if that's correct or not. So if I'm looking at what's over here, it kind of seems like I've got like two separate terms. So I've got some things being multiplied. I've got x plus 1 times 2e to the 2x minus e to the 2x. So I have like two separate groups and they're being subtracted. So I am allowed to pull things out of this. So I'm just factoring this and I'm seeing what do these two groups have in common, and I'm allowed to pull things out. So if I pull out, I'm going to do my own work below. So if I pull out e to the 2x, this becomes x plus 1 times 2. So this is the stuff that's left behind when I pull out e to the 2x, minus 1 over x plus 1 squared. Okay, so now it looks like the next step they did, well, first of all, everything's good on this first part. Everything's good. This is the same as what they got here, and we're all good. So for the next step, it kind of looks like they just multiplied what was like in these brackets. They distributed and combined things together. So let's just do that for ourselves. So if I'm focusing on what's in these parentheses here, this is equal to e to the 2x. I'm going to go ahead and distribute this 2 in. So this becomes 2x plus 2 minus 1 all over x plus 1 squared. Okay, so now this is e to the 2x times 2x plus 1 over x plus 1 squared. Is this the same thing as what they got? Yes, these are the same, so this would be correct. Okay, so let's talk about why 6 is incorrect. So if we're looking at the work here, the first step they did was it looks like they canceled out the x plus 1. So it looks like they canceled out the x plus 1 with one of the x plus 1s in the denominator. So does anyone have any ideas of why this is an incorrect move to make in this situation?
Does it have anything to do with the fact that, like, I don't know, it hasn't been officially like factored out in the denominator?
So you're kind of on the right track there. The x plus 1 is only like, if we're considering these as like two separate terms, the x plus 1 is only on the first term in the numerator. We don't have an x plus 1 on the second term, so we can't factor it out. So we can't cross cancel them out. So yes, it's kind of because like it hasn't been factored out of the numerator, because we can't factor it out. So I see that a lot in worksheets where like there's one factor on one term and it just gets canceled out. Or maybe like it's like 2 minus x and there's an x in the denominator and they get canceled out. So be really careful that before you cancel something out, you make sure that you can factor it out. So that's a really good way to phrase it. Factor something out and then cancel it out. If you can't pull it out of both terms in your numerator or both terms in your denominator, you cannot cancel it out. So just a little speech there for you on canceling out. Okay, so anyone have any questions on 6 and 7? Okay, so I just did 7. Good. I got 2 questions on drawing derivatives, so that's good. So we can do those. So let me look because someone else asked for 51 and I don't just want to avoid 51. So let me see what it is. Oh yeah, so we can do 51. Let's do 51 since that was asked a little while ago. Okay. So I'm just gonna do all of 51 because I feel like it would probably be helpful just to do the whole thing. Or do I just want to talk about it? Okay, well, let me just start it. We'll see. So 51. Okay, so below is a graph of f of x equals x times the square root of 25 minus x squared. Find the equation of the tangent line for f of x at x equals -3. And then it says draw the tangent line on the graph. Okay, so let's go ahead and do this. So I don't even know how many times we've done one of these problems in recitation. They're getting kind of old in my opinion. But here we are with another one. So I want you guys to just be so good at finding tangent line equations by the end of this class. I think that's the goal here because that's what it really seems like with these worksheets. So remember that we need 3 things when we are doing equation of tangent line. So we start with point slope form, which is y minus y1 equals m times x minus x1. And we need 3 things here. We need to find, so write this down. We need x1, y1, and m, but you will always be given x. You will always be told what x is, because if you don't know what x is, I mean, you can find the derivative, but you can't really do anything else. So you will always be given x, which in our case is -3. And then y1 is always f of x1. So once you know x, you can easily find y1 because it's just f of whatever your x1 is. So let's do that really quick. So let's do f of x1, which is equal to f of -3. So this is going to be -3 times 25 minus -3 squared is going to be 9. So this is equal to -3 times the square root of 16, which is -3 times 4, which is -12. So this is -12. So you can honestly do 2 of these steps here without any calculus. You're given x1 and you can find y1 by just plugging it into the function. So the step that really requires some calculus here is finding your slope, because your slope is going to require that you take the derivative. The slope of the tangent line at -3 is the derivative evaluated at -3. So the derivative will give you the slope of the tangent line at that point. So let me rewrite f of x just to make it a little easier for us to take the derivative. So this is x times 25 minus x squared to the 1/2 power. If you're ever given a square root and you got to find the derivative, always easier to write it to be 1/2 power because you know the power rule makes life a lot easier. However, this is a bit of a complicated one to take the derivative of because you've got a product rule. You've got 2 things being multiplied, but within this second function, you've got a chain rule. Yikes. Well, let's take it step by step. So f prime of x. So our product rule says, let's just leave the first function alone. So we'll just bring down x. And then we have to multiply it by the derivative of our second function. Okay, so chain rule here. Let's take the derivative of the outer piece. So our outer piece would be to the 1/2 power. So our power rule says I bring down the 1/2. I keep what's inside those parentheses, and then I subtract 1 from the power. So this gets raised to the negative 1/2. But don't stop here because the chain rule says that you have to multiply it by the derivative of this inner function here. So what's the derivative of 25 minus x squared?
Is it just negative 2x?
Yep, perfect. So multiply it by negative 2x. And then the next step in the product rule is to take the derivative of the first function and leave the second function alone. So we add to it and we take the derivative of x, which is just 1, and then we multiply it by 25 minus x squared to the 1/2 power. Okay, so let's do a bit of simplification here. So this is equal to negative 2x squared over 2 times the square root of 25 minus x squared. Plus, yeah, this is just square root of 25 minus x squared over 1. And then something nice here is that one of these, oh, not the x, I'm sorry, did not mean to do that with the x. This 2 cancels out here. So now we're just left with negative x squared over the square root of 25 minus x squared plus the square root of 25 minus x squared over 1. Okay, so what I've told people before is you take this derivative so that you can plug in negative 3. You want to evaluate this at negative 3 because we're getting our slope from this. So you have 2 choices here. You can either simplify this derivative and then plug in negative 3. And then once you plug in negative 3, it'll be pretty quick. Or you can plug in negative 3 and then simplify. It's up to you. I mean, really, whatever you want to do is fine. I typically just will plug in the number. So I'm just going to do that. So I'm going to plug in negative 3 to this thing right here. So let me just give myself some room. So f prime of negative 3 is going to be negative 9 over 25 minus 9 plus 25 minus 9 over 1. You can see I'm going to have to simplify this a little bit because I have, 2 separate fractions here. It's going to take me a little work to simplify it and make it nice. So like I said, you can simplify before you plug it in, or you can simplify after you plug in negative 3. Either way, you're still going to have to do simplification. So this all is equal to negative 9 over 4 plus 4 over 1. Okay, so now we have to add these fractions together. So to add them together, I'm going to get a common denominator. And this is negative 9 over 4 plus 16 over 4. And that is just equal to 7 over 4. Okay, and that means that our m is 7 over 4. Okay, so we have everything that we need now. But don't forget the last step. So you wanted to get the equation of the tangent line. So now we just have to plug in what we have to this y minus y1 thing here. So our final answer is y plus 12 equals 7 over 4 times x plus 3. And you are totally fine to just leave it like this. So you could totally use this to graph the tangent line. You could totally put this in y equals mx plus b form, and then you could use that to graph the tangent line. Or you could know that if we're graphing the tangent line at negative 3 here, it's the line that goes right under the curve, like that. Well, you could draw this a little nicer, sorry. So if you had some knowledge of what the tangent line was, you could just do that. Or you could totally put this in y equals mx plus b form and then just graph that line. So why don't we do that just to show you guys that you should get the same thing. So This is equal to y plus 12 equals 7/4 x plus 21 over 4. Let's subtract the 12 over. We get y equals 7/4 x. Let's see. So plus 21 over 4 minus 12. So that's 48, 48, 48 minus 21, 9 plus 18, 27. Make sure that's correct. I think that should be right, but let me double check myself before I graph this. Yes, 27 over 4. Okay. So y is equal to 7/4 x minus 27 over 4. Okay, this is a little ugly to graph, but we can totally still do it. So you could graph this line and you would get something that looks very similar to what I just drew. But if you have knowledge of the tangent line, you can totally just give a rough sketch of it on the graph. Okay, let me check and see. I got some questions. Ooh, okay. Let's do steps for drawing the derivative because I was asked that 2 separate times. Does anyone have any questions though on 51 before I move on? Okay. All right, so I'm gonna go over my steps for drawing the derivative. They're not super exciting. This is just how I approach drawing the derivative. So hopefully this makes sense. So let's do question 8 first. So they give you the graph of f of x, and you have to provide the graph of f prime of x. Okay, so the derivative of a function will tell us where the function is increasing, decreasing, where it has, maybe like a slope of 0. So we have to kind of connect what the derivative tells us about f of x so that we can graph the derivative. So the first thing that I usually instruct people to do is maybe find any spots on the graph of f of x where you think the derivative would be 0. So spots where the derivative are 0 is spots like this, where you have, like a min. Spots where the graph turns around, kind of flattens out. So this is another one here where it flattens out there. So those are 2 spots that I've identified that the derivative could be 0 or will be 0. So if you've got, some maximum, so it comes up and then starts going down, in order for your function to come up and then turn around, it's got to eventually, have a spot on top where the slope of the tangent line would be 0. That's a good way to put it. So maybe look at your graph and find spots where the slope of the tangent line at that point would be 0, aka a horizontal line. Okay, so I've identified 2 spots where that would be true. So here and here. So that is at an x value of -2 and an x value of 1. That's a good thing to start off with because then you can come immediately down to your graph of the derivative and you know that at -2 and 1, it will cross the x-axis. So those are some good points to start with because you have an idea of kind of, the behavior at those points. And then you can kind of just connect the dots. So the derivative also will tell you where your function is increasing or decreasing at. So something that's helpful to know for this is that if your function, your original function, f of x, is decreasing, your derivative will be negative. So I'm going to write this down because this is very important for doing these problems. So if f of x is decreasing, f prime of x will be negative. If f of x is increasing, f prime of x will be positive. So what that's saying basically is if the slope of f of x is negative, f prime of x is negative. That's because the relation is the slope. So the derivative gives you the slope of the tangent line at that point. So if your original function is decreasing, then your derivative will be negative. If your function is increasing, your derivative will be positive. So what I like to do is go along my graph of f of x, and I like to kind of label any spots where my function is increasing or decreasing. And then I just translate that onto my graph of f of x, or f prime of x. So I'm going to come along my graph of f of x, and I'm just going to start on the left-hand side. So if I come down here, this is decreasing, 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 decreasing. And when I say decreasing, I mean the outputs are decreasing. So this whole section right here is decreasing. Okay, and then I get to the spot where my derivative was 0, and then my function turns around. So then from here, I start increasing. Increasing, increasing, increasing. Awesome. And then I get to the spot where my derivative is 0, and then from then on, oh look, it's still increasing. Okay, so then I like to just translate this to f prime of x. So any spot where my function was decreasing, my derivative will be negative. Any spot where it's increasing, my derivative will be positive. So this doesn't need to be perfect, but you know that until your graph crosses this point, the derivative should all be negative, which is helpful because your function is decreasing all the way until -2. So let's just give it a rough sketch. It's negative, negative, but it has to come up here and hit that point. Okay, well, after -2, my function is increasing all the way up until 1. Okay, cool. So I know that my derivative has to be positive from -2 to 1, but I also know that it has to come back down. So I know that, let's say it looks something like this and it comes back down. Okay, well, after 1, my function continues to increase, which means the derivative is still positive. So it actually just comes up like this and just makes a little loop, or a little turnaround. So key takeaways, if the function is decreasing, derivative's negative. Function is increasing, derivative's positive. So that should help you at least get a rough sketch of the graph. Okay, so in questions like number 9, this one always tends to throw people off. But whenever you're given a graph and it's just a bunch of straight lines, it's just a bunch of lines. So you've got a line segment here, a line segment here, and a line segment here. So we can find the slope of each of those segments. So we have like 3 different segments that are connecting, and we can find the slope of each separate one. So we're actually able to technically find the derivative of the points on this function. Because remember, the derivative is just the slope of the tangent line. So we can find the slope of this line, the slope of this line, the slope of this line, which means then we know the derivative at all those points. So let's go ahead and do that. So there's a chat, so give me a second. The minus.
That was from a few questions ago.
Oh, okay, sorry, thanks. I was very confused. Okay, so I'm gonna go ahead and just do the slope of this first segment here. So slope, just like how you would do in algebra, is just like rise over run. So from this point to this point, so boom, boom. So I go up 1, 2, 3, and over 1. So that means that my slope is 3 here. I'm gonna do it for the next segment. So rise over run. So I go up 1 and over 2, which means that my slope here is 1/2. And then let's do it for this one. So I go to the right 1 and down 1, which means my slope here is -1. Okay, so this derivative function might look a little weird, but I know that from -1 to infinity, from -infinity to -1, my slope is 3. So what that means is I come up here to -1 and I draw an open circle here, and to the left, it's just a straight line. So let me explain this a little bit. So from -infinity to -1, my derivative is 3, and that's because the slope of that line was 3. But it's important to know that at any of these like points here where we switch, like segments, or we switch like the slopes here, we don't say that the derivative is 3 because the derivative is not actually defined at that point. So when you graph it, make sure that you graph an open circle here and not a closed circle, because the derivative is actually not defined at these like sharp turns. Okay, my next segment was from -1 to 1, and my derivative was 1/2. I'm just going to come over here and do the same thing, open circle, and it's at a value of 1/2. So if it helps, you could also like kind of draw a little chart and say like, okay, from -infinity to -1, f prime, or, oh, this one's g, sorry. G prime of x is 3. Okay, and then you could say, well, from -1 to 1, g prime of x is 1/2. That might help you graph it a little better. And then from 1 to infinity, g prime of x is -1. So maybe that would help you translate the points to a graph a little better. So for this last segment, we've got that. You could also make yourself a little chart. Maybe that would help you, you know, like translate it to a graph. But these problems are a little tricky. It's difficult to translate what you know about the function to the derivative. But the big idea is that the derivative talks about the slope of the tangent line, which, you know, will tell you if it's increasing or decreasing. So I guess that's like the big idea here. Okay, let me answer a question in the chat. So 1 second, guys. So, okay, I had a question on how specific your graph needs to be in regards to number 8. So, if you're looking, like I asked why, or I got asked why does f of x go to 3 on the y-axis for number 8, or sorry, why does f prime of x go to 3 on the y-axis? Yes, it's because of the slope. So remember that the derivative is just the slope of the tangent line. So if you went ahead and drew a tangent line on f of x where x is 0, you would see that that slope should be like roughly 3. It doesn't need to be like perfect, because drawing a tangent line by hand or something is like never perfect. Your tangent line might be slightly, you know, slanted wrong. So if you, I mean, it's kind of an estimate, but essentially it's like, okay, if you drew the tangent line on the original graph where x was 0, you should get something around 3, which would tell you about how high your slope should go on the graph of the derivative. Hopefully that kind of clarifies the question that I was asked. But it's not going to be like perfect, because like I said, when you draw the tangent line, you're not going to get like, I mean, I guess unless you pulled out a ruler on paper and you like really got it good, but it's not going to be like, okay. So let me check. Okay, that was the derivative. Hopefully, I think I can get through the last 2 questions. So number 14 and number 30. I have no clue what they are, but let me go. Oh yes, I can definitely do number 14. So let's go ahead and do that one. Okay. So these questions are just find the derivative of the following. So 14 is f of x equals 4 over x to the 5th. So this question might be throwing some people off because it might look like a quotient rule because you have a fraction. So you have like 4 over x to the 5th. You could totally go through the process of doing a quotient rule. I probably wouldn't recommend it. I would say to just write this as 4 times x to the -5 or -5th power. So that would be my suggestion for you. Is to just bring up the x to the 5th as x to the -5th, because then it just becomes a power rule. So then f of x is equal to 4x to the negative fifth, which means that x, or no, f prime of x is equal to negative 20x to the negative sixth, which is negative 20 over x to the sixth. So whenever you can make it easier on yourself and say, oh, hey, I can just bring up the x to the fifth as x to the negative fifth power, do it. It'll just make your life a little easier. So if you can ever manipulate what you're given to make the derivative process faster, it's always a good idea. But you could do it the long way, and you'll, as long as you don't make any mistakes, you won't get a different answer than if you did it like a shortcut way necessarily. Anyone have any questions on this one? Okay, so question 30 is a long one. I can probably get through 30 and that'll be the last question. But it's a good question to do. So let's do 30 because I think this was one that we did something similar in recitation, but I don't think in either class I did all parts of it and it's kind of confusing. So, and I'm almost out of water. So this is a good one. I am out of water. This is a good question to end on. You can tell my throat's like dry over here. Okay, so let me do question 30. Okay, word problems are just everyone's favorite, right? Okay, so the position of an object in meters moving horizontally at time t in seconds is determined by the position function x of t equals t cubed minus 12t squared plus 36t minus 5, where t is greater than or equal to 0. Remember, t is greater than or equal to 0 because it's time. So just keep that in mind whenever you're doing word problems, that you do have units now. So you have, seconds. So we're not going to say like -3 seconds. It's like, we're not time travelers here. So we're only working with positive time. So let's see. Question A wants the velocity function and then the velocity function of the object at t equals 1 seconds. So this is where you kind of have to remember the relationship between position, velocity, and acceleration. Hint, they are all related through derivatives. So velocity is the derivative of position. Acceleration is the derivative of velocity. Okay, so I'm going to write that down. So v of t is equal to x prime of t, because our position function is given up here as x of t. So velocity is the derivative of position, always. Acceleration is always the derivative of velocity. So let's go through that. So all we have to do is find x prime of t. So does anyone have an idea of what x prime of t is? So just the derivative of x of t.
Would it be 3t squared minus 24t plus 36?
Yes, perfect. So 3t squared minus 24t plus 36. Okay, great. So now you've found the velocity function. So v of t is equal to 3t squared minus 24t plus 36. Okay, well, that was part of the question. And then the next part just wants you to find the velocity of the object at t equals 1 second. So that means you just plug in 1 to the velocity function. So you just have to find v of 1, which is 3 minus 24 plus 36. So that is 15? Yes. Okay, 15. And then don't forget your units on the word problems. It's always what gets people. So velocity is given in meters per second. Okay, so B wants the acceleration function and the acceleration of the object when t equals 1 second. So acceleration is the derivative of velocity. So A of t is equal to v prime of t. Okay, so who wants to tell me what the derivative of the velocity function is?
6t minus 24.
Yep, 6t minus 24. Good. So that's part of our answer here. And the next part of the question wants you to find the acceleration at 1 second. So we're just going to plug in 1 again. So a of 1 is 6 minus 24, which is negative 18. And then acceleration is given in meters per second squared. Okay. Okay, so the next questions are now kind of asking you to almost like interpret the functions that you have and be able to use them. So C asks for the times when the object is stopped. Okay, so the object is stopped when the velocity is 0. So if the velocity is 0, the object's not moving, and that would be when it's stopped. So being stopped means that V of t is equal to 0. So we'd have to find where that's true at. So where is 0 equal to 3t squared minus 24t plus 36? Wait, is that the correct answer? Oh, yeah, it is. Okay, sorry. I thought I wrote down the wrong function. Okay. So we do need to factor this, but to make this easier on ourselves, we can pull out a 3 first. So this is equal to 3 times t squared minus 8t plus 12. And then this will be a little nicer to factor than what we started out with. You could factor what we started out with. You'd be fine, but I'm just going to pull the 3 out to make it like smaller coefficients on my terms here. So I'm going to factor this. So let's see. We need something that multiplies to 12 and adds to negative 8. So negative 6 and negative 2. So t minus 2 and t minus 6. Okay, well, this equals to 0 if either this piece is 0 or this piece is 0. So that means it's where t is equal to 2 and 6 seconds.
It might be silly to ask, but like, are we supposed to do anything with that 3, or we can just leave?
You can leave it. You could also, like, it's totally fine to also divide by it and say like, okay, if I divide by this 3, this is still 0. So that's 0 equals t minus 2 times t minus 6. It's totally fine to divide by the 3 and then just be like, oh, that's easier to look at, but you can totally leave it.
Okay, cool. That makes sense. Thank you.
Mhm. Yeah, I'm usually a fan of dividing by that number just because for some reason it kind of bugs me when it's out front. So I usually divide by it. Okay. D, the times when the object is changing direction. So an object is changing direction if V of t changes sign. Okay, so whenever you think of something changing sign, you want to usually draw a little sign chart. I think that's the most helpful way to visualize when something is changing sign. So our sign chart starts off as a number line, and it will start at 0. And that's because our time starts at 0 because we're not using negative time here. So t starts at 0. And then the other points that you label on your sign chart, I don't know, it doesn't matter, whatever. The other points that you label on here are the zeros of the function. So this is a v of t, so I'm going to put spots at 2 and 6. And the reason we do that is because we know at 2 and 6 the sign of v of t is 0. I mean, the sign, there's no sign of 0, it's not negative or positive. So you know at 2 that v of 2 is 0. And same with 6. You know, v of 6 is 0. Let me drop this here. There we go. So what you're concerned about is the sign in these in-between chunks. So what's the sign from 0 to 2? What's the sign from 2 to 6? And what's the sign from 6 on? So any zeros of the function are spots where your sign could change. It doesn't have to, but it could change. So what we do here to fill this in is we take a value that's between 0 and 2, and we just plug it in to our v function. So let's just do v of 1, because that's nice and easy. So What was V of t? V of t is, I'm going to write down the factored version because that's a little nicer. So V of t is 3 is t minus 2 is t minus 6. Okay. So if I plug in 1 to this, I get 3 times -1 times -5, which is going to be a positive number. So I write a positive here. You don't care about what the number is, you just care if it's positive or negative. So let's do V of 3 now for this second section. So let's plug 3 in here. So I get 3 times 1 times -3. So that's going to be a negative number. Okay, and then let's do 7 because 7 is like in our last section. So if I plug 7 in, I get 3 times 5 times 1, which is going to be something positive. Okay, so actually our sign would switch where t is 2 and 6 because it goes from positive to negative, then it goes from negative back to positive. So our object changes direction where t is 2 and 6 seconds. It may not always be both spots. It may just be one. Maybe it's none. I don't know. Because just because the object stops moving doesn't mean it changes direction. It could stop and then keep going the same direction it was already going. Okay, E is not too bad because E just wants to know the time intervals when the object is moving to the left. So if it's moving to the left, that means that V of t would be negative. So the left means that V of t is less than 0. Where if it's moving to the right, it means that it's greater than 0. So just using the chart that we did on part D, if V of t is less than 0, it's moving to the left. So does anyone have any ideas what interval does anyone have any ideas what interval the object is moving to the left? So where V of t is negative.
From 2 to 6.
Yep. From 2 to 6. And we never include the endpoints because at the endpoints, it's 0. So always, always open parentheses unless your interval is like this interval, because then you can include 0. But if your interval is like in the inside, it's always open brackets. And you'll see that on part F. Might make a little more sense on the next part. All right, last one. So the time intervals when the object is speeding up and slowing down. So this requires we have a sign chart for V of t and A of t, because if the object is speeding up, it means that the sign of V of t and A of t should be the same. So if it's speeding up, their signs are the same. If it's slowing down, their signs are opposite. So speeding up is sine, like an H, sine of V of t and A of t are the same. If it's slowing down, it means that the sign of V of t and A of t are different. Okay, so I'm going to just copy my sign line down from part D. So for V of t, I have this. Use a different color. Oh, should be a plus sign, I think. Okay. Positive, negative, positive. Okay, and then let's do one for A of t as well. So I'll do this one in a different color. The same thing, it starts at 0, but something that we need that we don't have already is the zeros of A of t. So let's go up quickly back to where we found A of t, which is this function right here. And let's just find the zeros of this function. So set it equal to 0. So solving for t, that means that the only 0 of this function is 4. So remember, when you're doing a sign line, you need to know the zeros of your function because those are spots where the sign could change direction. So the only 0 of A of t is 4. Okay, so that's nice. All we have to do is fill in the sign for 2 intervals here. So for this first interval, I'm going to just plug in 1 because that's You know what? Let me copy down the VFT function or the AFT function. I don't have it. So A of t is equal to 6t minus 24. Okay. So for my first interval, I'm going to do A of 1. If I plug in 1 here, I get 6 minus 24, which is negative. Okay, and then for my last section, I'm going to do A of 5. If I plug in 5, I get 30 minus 24, which is positive. All right, so you're almost done here. Now you just have to identify spots where the sign is the same and where the sign is different. Okay, so let's see here. So, okay, right away, I noticed that from 0 to 2, V of t is positive, but from 0 to 2, A of t is negative. So you can see for this section, it's positive, and then, you know, if we just, 2 is like right here, this is negative. So I see that they have different signs from 0 to 2. So let me just write this down. So it's speeding up and then slowing down. Okay, so it's slowing down if they have different signs. So like I said, V of t is negative from 0 to 2, and A of t is, I'm sorry, V of t is positive from 0 to 2, and A of t is negative from 0 to 2. So that means that it's slowing down from 0 to 2. All right, take my highlighting off now if I can. Okay, and then I noticed that from 2 to 4, they actually both happen to be negative. So from here, it's negative, and then 4 is like right here on this one, and it's also negative. So from 2 to 4, they're both negative, which means that it's speeding up. Oh no, I erased my line. Dang it. Okay. Oh my gosh, trying just to erase the highlighting is like a sprint. This is okay. The next thing that I want to look at is that from 4 to 6, V of t is negative, but from 4 all the way to infinity, A of t is positive. So they have different signs from 4 to 6, and if they have different signs, it means that they are slowing down. So 4 to 6. Lastly, they are both positive from 6 on. So from 6 to infinity, they are both positive, which means they are speeding up. So a little hint here, if you notice, if you look at what I've written down for speeding up and slowing down, if you were to like look at all those intervals together, they actually cover the whole number line because we have from 0 to 2, it's slowing down, then from 2 to 4, it's speeding up, then from 4 to 6, it's slowing down, then from 6 on, it's speeding up. So when you look at all these intervals here, you should cover every point on the number line. Just a helpful tip. So if you know that it's speeding up from 2 to 4 and then from 6 to infinity, any of the spots that you haven't covered, it should be slowing down at. You shouldn't have any of the same intervals for speeding up and slowing down because it can't be speeding up and slowing down. And you should cover everything on the number line between where it's speeding up and where it's slowing down. Okay, so that is my speech. I am now 10 minutes over, so I'm going to stop sharing my screen now. But thank you guys for all coming. This was actually really good. A lot of people came, so I'm excited. So good luck studying for your exam, and I'll see some of you tomorrow. So have a good rest of your night, guys.